So today, David and I are going to explain a little bit about how the devices that you use now are working, and then what you can possibly look forward to in the next generation. So I'm going to talk about batteries and supercapacitors, and David's going to talk about fuel cells. So right now, probably every single one of you in your phone and your laptop, all of these are operating on literally the exact same 30-year-old, pretty boring and not that good chemistry, which is lithium cobalt oxide. So we'll talk about that in a minute, and we'll talk about why they're all operating on this one chemistry when we have so many others, and when things might start changing. So the mobile electronics, this stuff will play a big role in that, but so we're talking more than 1 billion batteries a year. So whatever we make these out of, we need quite a bit. And then moving forward, we're going to start seeing even more electric vehicles. So right now there's a $5 billion factory going in just for Tesla Motors itself, and in addition to the other companies which are making these electric or hybrid electric vehicles. And for solar and wind, another future application of batteries where they're going to be really important is for renewable energy technology. So these can only produce energy obviously during the day or when it's windy. And if you want to have power at night and not go through these fluctuations all the time, you need basically battery storage. And so what you'll often see now when they do have like these wind farms and stuff, they'll have these big, basically they'll just look like semi-trucks, like beds parked next to those, and these are basically full of batteries. Just massive battery storage things. And so the term they'll use for it is load leveling. And then we have to think about how we're going to do this. So for batteries, it's basically a solid-state chemistry question. But it's a hard question, and that's why we're still using an old technology that we know isn't very good. Because it's the devil you know, not the one you don't, even if the one you don't is better. For supercapacitors, it's pretty straightforward. Just a lot of carbon. A lot of carbon from a lot of different places. But that story is less chemistry, a bit more physics maybe. And then fuel cells, one of the main advantages they have is you can put in almost anything, as far as David tells me, into a fuel cell and run it. Yeah, so that's what he'll try and convince you of either, as well. So I'll talk first about batteries and how they work. So what you have now, this is literally what's in everything you have. You have a graphite anode, which is the blue, represented blue on the left, and a cobalt oxide cathode on the right. So the reason that so when your phone's discharging, the reason it's giving you energy is because the cobalt oxide wants the electrons and the lithium that come with them more than the anode does. It's pretty meh about having these electrons. Whereas the cathode thing, he's super excited. So in this layered cathode, basically, in this picture, which is really small, there's these lithiums in pink, and basically they're just going in and out of the layers of this cathode, and that's really as simple as this reaction is. So I've written some reaction mechanism. It's just lithium going into this layer and then lithium coming out of it. And it's the same on the anode side. But there are much more complicated things. And so your lithium goes straight through this electrolyte in the center. This goes back and forth, but you force the electrons to go through some device, so either through your phone for Snapchat or through your car. And so this is what actually does the work. The two main different types of chemistry that are present in this are, I've shown on the right, so either this phase change chemistry, so that basically means you have one compound, and then it turns into a completely different one. There's nothing in between. So like, you could have like lithium cobalt oxide going to cobalt oxide. It either like has one full lithium in this whole structure, or it doesn't. But you could also have solid solutions, and so that's what's shown in this lower curve. And then a solid solution chemistry, it just means you can have any concentration of lithium inside of this, and it's still happy. So it could be 50% lithiated or 75% lithiated, and it's still happy. And so these kind of chemistries dictate a lot about how the battery works, whether it has to go from X to Y or whether it can go between everything. So how do you make a battery? That's a good question. So in this highly technical diagram of pictures I took with my cell phone, you with this stupid cobalt oxide battery in it, you make a bunch of powders. So in this case, those are just a variety of some metal oxide powder that I made. And then you shoot X-rays, this is what X-rays look like. You shoot X-rays into, and this is in an X-ray diffraction sample holder, and to make sure that you made the compound that you think you did. That's pretty important. And then in a mortar and pestle, you can grind this up with some carbon because you need usually something that's more conductive than what your metal oxide is or whatever your compound is. So you mix in some carbon with it, and then you mix in some polymer to bind it all together, and you make it into a slurry. And so on the right, so I basically just added some liquid to that, made it into a slurry, and then kind of just spread it evenly over this aluminum foil. You then use the hammer of science to, in a highly technical way, take this little press onto this board and just smash these cathodes out of it, and then they turn into these nice, pretty little circular cathodes, which are here and here. So relating back to the picture I showed you earlier, this is just your cathode. So this is when those have been mixed together. And then this is lithium metal. So this is your anode. And they have this separator in between. And the separator is what you fill with some lithium-like electrolyte and goes back and forth between that cathode and anode. And the rest of those pieces are just parts of the cell pulled together. And then you get that superhero battery cell. That picture of a battery with a cape on is actually from a Nature paper. Gotta make batteries more exciting, you know, like, gotta really get the people going. So this work is super cool because this was done by a 4th-year Churchill student, actually. You probably none of you know, but his name's Hao Lu, and so he's at Churchill, and this work got published in Science a couple weeks ago. It's pretty exciting stuff. So this is lithium iron phosphate, and so as I said, you all have lithium cobalt oxide now, but this is probably the first thing that you'll see next. So there's already many companies who are, and a few different people have patents on it, other people are licensing them, but there's many companies already building batteries with lithium iron phosphate in it. There's quite a few advantages to it. One is that unlike having cobalt, which is pretty rare, pretty expensive, and pretty toxic, this basically has iron substituted in. Iron is ridiculously cheap and abundant and much less toxic. So so these iron-based batteries are really advantageous. And what Hao has been working on, so I've shown the crystal structure, and don't worry about it too much, but basically the green things are lithium, and it's just showing there's all these one-dimensional channels, and these are what the lithium are going in and out of. So unlike the layered compound we looked at before, which had just going through these two-dimensional layers, this is just going through these ion channels. But interestingly, even though it's only going in one dimension, it goes faster than it did in the cobalt ones. So you might actually see these batteries be faster and be cheaper. And that's pretty cool. But what Hao's work particularly was on was trying to understand whether this was some kind of solid solution or whether this was a phase change reaction, and really figure out the mechanism behind these batteries. So what he showed here is somehow we're going from lithium iron phosphate to iron phosphate, and then we just go back and forth between these when we put lithium in and out. But how are we doing it? And so some people in the past had proposed, so maybe the lithium iron phosphate completely loses its lithium and then turns to iron phosphate. So that section loses all of its lithium at a time. So this would be the two-phase reaction, right? This would be this phase change. It can't exist in between. And then there's also this option here, which is more like a solid solution. So if we ignored the middle and just looked straight at the top, this would be like a solid solution. So we have things that are all the way lithium iron phosphate, and then they kind of go between. And what Hao found, which was actually really interesting, is that it's not exactly either of these. So it goes through like a non-equilibrium solid solution. But all that means is they can go into this in like any quantity, but they pretty quickly relax. So they go into it in some, that means they can go in any amount, but then they relax to form these structures which have more defined compositions. So it's, basically it's more complicated. It's in between, things we had thought about in that more classical model of one or the other. This is a mixture. And then, so we'll get into like a couple more futuristic things here, but they're really interesting. So this is silicon or silicon nanowires. So instead of using, so some things like the lithium iron phosphate I showed you, those are for the cathodes, but we do research on both the cathodes and the anodes because we want to make both better. So this is an anode, and so this would be replacing like the graphite. So graphite's obviously really cheap, but it's really crap. And so you want something that is equally as cheap, but it works a lot better. Silicon's pretty cheap. It's the most abundant thing in the Earth's crust except oxygen, so that seems like a good place to start. And it has 10 times more energy storage, which in theory means you might charge your phone once a week or something. I'll tell you later why that will never happen. But in theory, it could work like that. The bad part about it is that it has a 400% volume expansion. And the stuff we can deal with right now is generally like 5%. If it's your phone now is probably like 5%, right? So we can deal with that because it's a lot easier. And so that's why rather than even saying silicon, I've already just called this silicon nanowires, because you can't just stick in a chunk of silicon. It doesn't work. So you have to come up with something, some geometry that's more sophisticated. And right now the thing that's working best are sort of these nanowires, because you imagine if you grow this, like these mesh of nanowires as these images show, those things might be able to expand 400% and still be stable, right? If you just put in a block, the whole thing's going to break up. And it's no good. And there's a big paper recently where someone actually made these things just from beach sand. So they found a way with some pretty inert chemistry, some pretty green chemistry, to convert actual just beach sand from wherever the beach is closest to UC Riverside, and make these nanoparticles by like leaching out the oxygen and making it into these porous nanoparticles. So there is a possibility for this, and many people are working on it, including people in our group. And then one of the other big ones, and so this is the one I think will be, my prediction will be the one that's going to revolutionize cars. So lithium sulfur is basically like the second most promising technology. You can kind of see that from this chart on the right. So lithium sulfur is here. So we're here now at this blue lithium ion, whatever. Lithium sulfur has the possibility, realistic possibility of going 2, 3, 4 times higher than that. And that's kind of what we need to see wide-scale adoption of cars, and cheap cars that have. There's no metal in this at all, basically. I mean, there's casings and stuff, but there's no rare metals. There's nothing like this. It's just lithium and sulfur. And it has really high capacity. It's very cheap and abundant. The problem is that the chemistry of it is quite complicated. So these sulfides that form on the way, so you have like just sulfur at one end, and then like lithium sulfide on the other end. But there's all these intermediates that have different compositions of lithium and sulfur. So it turns out neither thing at either end of the charge and discharge are soluble, but kind of everything in the middle is. And so if things like dissolve into your solvent, then you get like short circuits because they form reactions throughout the separator, and this is quite complicated. So people are working on how do we maybe find different solvents or different ways to set up the cell so that we don't have these problems with solubility. And just one of the images I've shown is just working on different geometries. But this is something that is also fairly close to market, and something that you are likely to see implemented in the future of and so since this stuff's so big and so cheap, rather than being in like phones or something, it's more likely to change what we're doing with cars. So that's pretty cool. Something that you'll probably never see is Lithiumair. Lithiumair batteries represent sort of the holy grail of how much energy we could store. So if you thought about it in an ideal way, the air that you could bring in would actually never have to exist in it doesn't have to be part of your cell as you drive or something. It could just come in and go out. So its weight would be 0, and then its theoretical capacity by weight would be infinite, which is pretty good, right? That's like at least 10 times better than what we're at now. There are some pretty massive problems with Lithiumair, one of which is that Lithiumair is a misnomer. This is lithium ultra pure oxygen, not air. If you put air in this, it won't work for 1 cycle. If you put ultra pure oxygen in, it will work for a few. And so, so one of the things on maybe this other plot I showed you so I didn't explain this really yet, but this bottom plot, the bottom part of the curve is like as you discharge, it's how much potential you get back, and then as you come back up to the top, it's recharging. So if there's a gap there, that's kind of the overpotential. So that's how much extra energy you have to put in, which is basically a loss. That's bad for energy efficiency. This is what the one for oxygen looks like. It's way worse. It's basically double. So you're basically losing half the energy every time that you put in anyways. That's not even close to the only problem, but it's only like basically half efficient right now. So people are studying catalysts because in an ideal system, like there's nothing really limiting that process. So with a good catalyst or something, you could have that better. Currently, the very best, most optimized ones you have will only last at all for like 20 or 30 cycles with ultra pure oxygen. So that's not really something that you could put in a car or in anything. And so it gives you these really long, like the first cycle will give you really long life. And if that were reversible, but what happens is, the good question to ask would be, okay, why? Why does it stop working? Why does any battery stop working? And one of the reasons is, and especially in this system, other reactions happen. Things besides the ones that you're shown of what should happen, happen. And so these generally degrade the system. So in like the battery you have now, it might be like things with the electrolyte react and they form these surface coatings. With the Lithiumair system, it's basically similar things. The electrode that it's on just gets clogged up with all these side products. And so you have to limit the side chemistry from happening. If you use real air, that's why they would stop working so much faster, is because real air would just have that many more side reactions that happen. And there's already ones going on. This image stuff on the side is, I wouldn't worry about too much, but this is the research that we're doing in our group with like solid state NMR. And it's just because we can see some of these side products that are happening. So besides the lithium peroxide, which is the blue plot, all these other colors represent things like lithium hydroxide, lithium carbonate, lithium formate, and all these other side products that we don't want to happen. And if all these form on one cycle, that's why after 10, the whole thing's dead, basically. So Lithiumair is questionable whether it will ever be a thing, but it's really interesting, and it obviously has a lot of potential, right? It has a lot, I hate that word, has a lot of possibility. Potential's a battery talk, unless you mean that's my bad. Obviously the coolest thing we're going to see today is what I'm studying. So we're finally here, you've all been waiting. The niobium oxide, those cool powders I showed you earlier. Niobium oxide itself, I don't know if this is something that will ever be something that you have to think a lot about, but high rate battery systems like it, I think will be something. So niobium oxide is a possibility. It has some of the issues, like it's as abundant as cobalt, so you could use it for what people use cobalt oxide now, but it's not like iron and it's not like sulfur, right? It's not everywhere. But for things like mobile electronics, what it represents is the possibility to do things like recharge your phone in 30 seconds or a minute, which is nice, right? Versus a couple hours. So like while I'm on this slide, you could recharge your phone. And it's extremely efficient as well. So its overpotential is not like the oxygen one on the last curve. It's very close. And so this is something, again, like for these kind of technologies, we could use it. So what this plot here shows, which is kind of complicated, is just that it shows that these are just different rates. So this one represents like 10 hours, and this one represents like 5 minutes. And so even going between 10 hours, and so that's how long you recharge it for or something. So going between 10 hours and 5 minutes, we're getting almost the same amount of energy. And you can actually make these numbers a lot better. This is in like a really basic system. If you make it more conductive, which is one of the things I'm studying, it can be a lot better. So that's the improving conductivity. It can make the speed a lot better. And so this 60 C one, which here is quite bad, that's 1 minute, or actually like 30 seconds when I ignore that. Everyone but David will argue with it.
I don't even know what's going on, so it's okay.
Good. It's a good sign for the room. Anyways, so we can do these things in like less than 1 minute, and if we improve the conductivity, we can get like big charge storage the same as what your devices have now. So that'd be pretty cool. Basically, same thing you have now, charge in 30 seconds. Good stuff. These images are just like the different powders that I showed you before. These are like high resolution SEM images of them, so you can see what they look like on a few micron scale. That's just pretty pictures. And so one bit of science that I want to introduce on this, since it's what I do every day all my life, is why are these things so much faster, right? It's just some other metal oxide. What is it that makes lithium cobalt oxide so slow? Why can't you recharge your phone now in anything less than 2 or 3 hours? And why couldn't you do it in a minute with something like this? And so the difference is really, it's what kind of environment these lithium ions are going into. So in lithium cobalt oxide, it's this structure, and the lithiums are the things in green. And so if you look at them, if you imagine taking all these things out, you could kind of see that the structure would collapse upon itself, right? They're actually holding this layer open. If you took out all these green blocks, the blue stuff would collapse on itself, and it would be unstable. So actually, even in your phones now, you never take all of these out. You take about half out. And so when you charge and discharge, your phone has something in it that tells you, okay, I'm half out, you got to stop and go the other way. And so this is what, and so also then they're propping it open. You can imagine if you had to go in and you have to hold something up, this is not such an easy process, right? In the niobium oxide that I was just showing you, there is nothing like this. So when the lithium go in, they go in between this layer here, and there's no expansion and contraction. They can be fully there, they cannot be there at all, and the structure is just as stable either way. And this also means that when they're moving in between, since they're not holding anything open, they can basically move around freely. Like they can move around just like a liquid flowing through something. And so we've made some cool measurements that show these have some of like the lowest diffusion barriers of anything. And that at room temperature, they're basically moving freely. And so this is essentially why these are so fast. And so not only then, so now we know this about niobium oxide, so now we'll want to look for other systems that maybe can do this as well. Maybe something more abundant than niobium, but it's cool that we understand how, like what makes a system able to charge and discharge in 1 minute. I think we're gonna, nope, never mind. So then the other, just to lump together all other like future battery technologies, is if we're gonna do something other than lithium. So like the things I talked about, okay, it's great if we can replace cobalt with iron or sulfur or something, but we still have lithium in everything. Lithium is super conveniently located in like the hills of Afghanistan. Like besides it not being that abundant, that's where like 90% of the world's supply is, which is really nice. But if we wanted it, you know, if we wanted to use something that were maybe a little bit easier to access and a little bit more abundant and cheaper, we would look for things like sodium, magnesium, calcium, aluminum. There was no way to fit magnesium into this pun, by the way. Like, I couldn't do it, just if you're reading that. I tried.
OMG.
I should have done it. It didn't fit naturally. But, so if we could use these things, obviously they're going to be cheaper, obviously they're going to be abundant, and some of them will actually even theoretically give us more energy, because each ion might hold 2 or 3 electrons. The only issues holding us back in these technologies are the cathodes, the anodes, the electrolytes. All the parts of the battery. Other than that, though, like we can still use the same casing on the outside, probably. Although I think the magnesium reacts with the stainless steel. Maybe the casing. But besides that, like, so these are something that I kind of lumped all together because, but there is research going on in these. I mean, sodium is the closest. There are sodium batteries that work. Magnesium is super far, and the others are not really existent yet. But these are things people are thinking about because these are directions, if we wanted to move away from lithium, that we might want to go. And now, yeah, we're going to do a couple quick slides on something totally different. So that's batteries. That's what you have now and what you might see next. Supercapacitors are a lot simpler in terms of their chemistry. It's just carbon, right? So that's cool. And the way they hold charge, or the way that, wow, that thing that I stole from Wikipedia moves around. I did not do that when it was on my computer. Awesome. Okay, so what you see here, rather than having like different cathode and anode, you can still think of them like this, but it's just carbon on both sides. So the cathode and the anode are the same. We might call this symmetrical, and it still has some separator in between. But what happens is this carbon has all these little tiny pores in it. And so it would be just like charging a parallel plate capacitor, where if you charge one positive, the other one will go negative. You can remove the voltage, and they'll still hold that charge, right, until you release it. So you can store energy. That's storing energy. In these, it's basically the same. You charge one carbon electrode, positive, and the other one goes negative. But also, because there's an electrolyte present, the positive one, all the anions in the electrolyte will go to that side. And so there will be a double layer of charge. These are called double layer capacitors. Fancy name. And so that's sort of what you're seeing here, is if we charge this carbon particle positively, the negative ions are going to kind of go around the surface of it. And so you get, but this is really significant, you get like 10 times as much charge storage. Because it isn't really just one layer, it's a couple layers. And so you can get really high charge storage. And so this electrolyte that you put in could be, I said, it could be like table salt, right, in an aqueous electrolyte, but it could also be the fun tetramethyl ammonium tetrafluoroborate, which is actually what we use in most of them. And then the carbon that you use is super important. So the carbon that you use is the research that a lot of people are doing, because all carbons are not even close to the same. The one that's conveniently spinning is diamond. It would literally do nothing. But people are using things like you want something really porous. You want something that has these small pores, and so people are thinking about using graphene, which doesn't really have pores, but maybe it could like line both sides of the surface or something. People use nanotubes. People use, these are called carbon onions, but people come up with other fun, stupid names for them. This plot here is from Celine, or this picture. This is just a disordered carbon, which in reality is what most of these are. So most of these aren't some nice ordered nanotube. They're literally just disordered carbon. And that's one of the things that, like, from our group is interested in mechanisms, is hard to study. How do you study something that has no order to it? Or does it have some, even if it doesn't look like much? And so there's people, that's just a picture from a molecular dynamics simulation. But the research side of things, so this was a really big breakthrough that came about 6 or 7 years ago and really brought supercapacitors into real use. And so what people thought, these white dots, they thought, okay, as your pore size gets smaller, it's 2, 3, 4, 5 nanometers, and those are good pore sizes, because as it gets smaller, probably it's going to keep getting like less and less, and so maybe we should use something that's like 3 nanometers or something as a pore size. Some other, and because that's about what an anion with, or a cation with electrolyte around it, with solvent around it, that's about like, whether it's water or whatever, that's about 3, 4, 5 nanometers. So they thought that's good. And what they found out though is if you use even smaller pores, so if you go less than 1 nanometer, which they just thought the ions won't fit in at all, so it won't work. Actually, the ions will desolvate. They lose their solvation shell, which is pretty surprising, I think, at the time. And so that's why this whole traditional view was changed. So the capacitance shot up in this red plot because, like, as you get closer to the surface, the amount of charge that's stored is also higher. That's just that's how a capacitor works, right? If you can get the capacitors closer together, they hold more energy there because they're. And so this is the same principle. So now these ions are even closer to the surface because they've gotten rid of their solvation shell, and you can have higher surface area because you have smaller pores. All these kind of things. So this really revolutionized the ability to use carbon supercapacitors, and now in some buses and stuff, I think in Shanghai, and probably you'll start to see this more and more. They have these supercapacitor buses because these are great for something where, like, okay, so the bus travels maybe a few miles or a part of a mile or something, and then it stops, and these things actually recharge the supercapacitor in it. So you just put in a burst of electricity, and then the bus goes to the next place. So the supercapacitors are quite big, so you couldn't use them, they would never be in a car or something, but like in a bus where you have a big platform for them and you only need them to go a mile or 2 miles without it, these are really great. And so this bus would have no emissions ever, and would never have to like refuel, anything like this. So those systems are already coming into place. I think that's my last slide.
Yeah, sure. Okay. So, I guess, yeah, we'll do questions at the end. Unless anyone has
I answered everything you want to know.
Well, yeah, that's definitely true.
All right. You might have to go faster than I did.
Yeah. So, okay. I'm in the same college. I have the same advisor. I work in chemistry. I'm basically the same person as Kent. Except Kent does batteries and I do solid oxide fuel cells. And Kent's already talked about all the really exciting stuff, so I'll just talk really quickly about fuel cells. So I've got up here the schematic of what a fuel cell is. Again, I've got a cathode, an electrolyte, and an anode, just like in a battery. The major difference is that I have some kind of a fuel flowing over the anode, and in this case air or oxygen flowing over the cathode. So these will only produce electricity so long as you have fuel on one side and air on the other. As soon as either of those is gone, no more electricity. So how this actually works in practice, we have oxygen here. It dissociates to form O2 minus anions. These propagate through the electrolyte, react with the fuel, in this case to form water, and that generates electrons that then drive the circuit the rest of the way. What this actually looks like, I want you to think of this as like a piece of pottery or like a ceramic that's just been chipped off, like from your mug or something. Because that's what this is, it's completely solid. The cathode, the electrolyte, and the anode are totally solid. And that's actually a bit concerning because I don't think in public consciousness there's not a good conception of solids conducting electricity. Maybe you think of a wire conducting electrons, but you don't think of a solid as conducting oxide anions like this. But it turns out there is some history to this. Faraday, way back in the 1800s, took these incredibly toxic chunks of lead fluoride, put them between two bits of a battery, and nothing happened, except when he heated it up to 300 Celsius, which is also very dangerous to do, these would now start to actually conduct electricity. And they would do so because these fluorides would propagate through the structure. He had no conception of this at the time, but he was actually producing the first solid electrolytes. A bit later on, Walter Nernst, a pretty famous chemist, came up with this awesomely named thing called the Nernst Mass, which is just literally, it's a bit of ceramic. It's a zirconium yttrium oxide. And again, he didn't really know what to do with it, but he stuck it in this Nernst lamp. You heat it up to about 500 Celsius, you apply a current to it, and it produces this lovely orange glow. And for a long time, up until about the 1920s, these were actually considered to be direct competitors with the light bulbs that were being produced in America at the time. And then they found out, oh, actually, it's not feasible to heat them to 500 Celsius every time. Because you'd have to, every time you turn on the light, you have to heat it up to this temperature. And then when you want to turn off the light, you have to cool it back down. So no, this didn't work. But we still managed to use this technology. In every single motor vehicle, that by law, it's required now, that you have an oxygen sensor in the vehicle. And it works by the same technology. You have this oxide ion conducting membrane. You have some sort of a reference air on one side and an exhaust gas on the other. And this is just used to measure the fuel mixture, how much gasoline you have in your exhaust, how much petrol, and how much air you have. And this generates a voltage based on that relative ratio. So again, going back, this is essentially, this first commercial SOFC, solid oxide fuel cell, is identical to what you have in every single car today. Oxygen dissociates, propagates through, and reacts with the fuel, generating electricity. The major problem is that these only conduct electricity at these temperatures, 600 to 800 degrees Celsius. So that means this isn't going to be something that you have in your phone. You're not going to be carrying around something that does that. And you have to charge it, and you have to heat up and cool down every single time. That's not going to happen. So this is sort of a very niche application. I'm going to skip through most of this, I think. But just let it be said that there are various kinds of materials that people have been studying to try to optimize the way in which the oxides will conduct through the structure. So this guy, Ishihara, in Japan, 20 years ago, found a very highly conductive material, which is based on this cubic structure. And later on, this was actually done recently at Cambridge, we found that we could use proton conductors as well. And this is something that in our group is working on this. I'm going to skip ahead just to my work really quickly. The other way in which you can conduct oxides through a material, so the red things here are the oxygens. In this case, in my work, the gray is the nickel and green is the lanthanum. Normally, oxide conduction happens through material. You have vacancies in the material, so you'd have like an oxygen missing here. And this oxide would then hop from one site to another, all the way through the material. Instead, in this material, which makes it very interesting, you have these interstitial oxide anions that form in these layers. And the oxide anions can just actually propagate through these layers, which means that they operate at much lower temperatures. Good if we're trying to make this technology functional. And it's much faster oxide ion production. In terms of what these things look like when they're put together, it's easier if we usually have this cathode electrolyte and anode as this planar fuel cell. We then stack a whole bunch of these together. You have some kind of a fuel source on one side and on the other. You package it all in this nice refrigerator-sized box. And then it goes, for example, on this truck or on this lorry. So this is an auxiliary power unit produced by Delphi. It's now recently been commercialized. And this would just be an additional way to have a reliable fuel source. It's much more efficient than a combustion engine. Combustion engines only use about 20 to 30% of the chemical energy in the fuel. Whereas solid oxide fuel cells can use half of that or even up to 3/4 of the chemical energy there. So they're much more efficient. A bit niche though. Other places that they've been used recently, Google has, I think, a solid oxide fuel cell stack there that they use for remote, sort of this very reliable power production. And I think the most niche application that I've seen is it's actually been used by the United States military in these drones, these unmanned aerial vehicles that have been deployed in Afghanistan. And so the idea is you have this solid oxide fuel cell in here, SOC, powered by propane. It guzzles about 112 gallons of propane every hour, but the really nice thing is because it's using this high energy density fuel, it can stay up in the air for 8 hours at a time. Whereas before, with the lithium-ion battery technology, I'm sort of dissing Kent's work now. It could only stay up at 2 hours at a time. So the real advantage here is that these allow you to use actual very high energy density fuels and much more efficiently than a normal combustion engine would allow you to do. And if you get a chance to look up the video for this, because the US military has a really funny video where they're like hunting down somebody, and I would play it, but okay.
Do you want to put up this slide?
Yeah.
Hold on. I told you I would answer things that I don't want to leave unaddressed. So the question that I wanted to end with is, why don't we have these things in our, so a lot of the chemistries I showed you now are really like future, but in that last 30 years, there's still been a lot of new chemistries discovered and things that are well established. Why aren't we using them now? And there's two main points to that. One is that, as I said, whatever we use, we want to make about 1 billion of a year, at least. And so the question the companies ask themselves is, do I want to put 1 billion of something in someone's pocket and then not know if it might explode? And so we already know that these cobalt oxide ones don't have a perfect safety record. But we know what causes them to have problems, right? So we can, they're not great in like any way, but we know what they're going to do. And that's honestly the reason, right? We know what they're going to do. So if you're going to make 1 billion of something and you're going to put one in every single person's pocket at home, you want to know how it's going to behave. And then with some of these that's basically the biggest point to consider, is that if you want to make this many and you want to go into that, it's going to take a long time to do, and it's going to take you a really long time to understand the safety and the chemistry behind that. So there's a lot of new things that we know work better and that we could use in small applications, but before Duracell or Energizer or someone else adapts them, or before the phone companies adapt them and put them in cell phones, the testing that they have to go through is extreme. So when someone comes out, and I know like people in general are annoyed by this as well, when the testing comes out and they say, oh, I made this battery that works X and it's better. Okay, and then you ask, why am I not using it now, and why am I not going to be using it next year or the next decade? It's for reasons like this. It's because, and they're not lying, they do make these things that do work that much better. Well, sometimes they're lying, but usually they're not. They might have a good point, but there are a lot of things that change, especially in this industry, between the lab and the industry. That's the biggest one. And yeah, so then I just want to thank you for your attention.
Any questions? Yeah. Fire away.
You said about side reactions in the batteries. Do you have ways of controlling them, or how to accept them?
No, that's the idea, is how to control them. So people do a lot of things. And so like in these Lithiumair systems, they try and use different catalysts that catalyze, because a catalyst catalyzes some specific reaction, right? So they try and use one that specifically catalyzes the reaction they want. Or like, what most batteries form is they form some kind of film over the cathode or the anode, really, but and this is kind of a passivating film leads eventually to these things degrading. And so there's additives you can use that will just basically prevent these side products from forming, or if they form, they'll redissolve them or something. So sometimes people use these additives. There's also like, yeah, and then sometimes they'll put their own coating on it first and say, okay, I know if I put you in there, you'll form some stupid coating I don't want. So I'll put a coating now, and then that might prevent another coating from forming or something. So you put something different in.
Is it an issue to do with the purity of the material, or will they have to be?
Not usually. No, it's usually just because chemistry isn't pure, right? The chemistry reactions don't happen to completion in one direction, one reaction often. That's not It's not a thing that outside of textbooks really happens. So in these electrolytes and these solvents and these materials, actually, they all start very pure. Because, I mean, yeah, if you use less pure things, you would have even worse problems. But even pure, that's not what really leads to the issues. Dave?
Yeah, I was going to say, so you said you put lithium cobalt. You said that you wouldn't want to put the lithium cobalt oxide into everyone's pockets because it might explode or it's not perfectly safe. Like, what would make it explode?
Oh, yeah, so when these things explode, it's because, so like with the Boeing ones, when they had that whole fiasco and stuff like that, these things happen because you form some, so the lithium metal, or basically you form some connection between the cathode and the anode, and so you create some short circuit. So these things called dendrites, which are like little trees or whatever that grow off the top, little branches, will connect those two. And if you do that, then you're just rapidly heating this. And there is an organic electrolyte, like there's some solvent in there. And this solvent, if you heat it, they're usually like, will basically form a gas, and that gas is what leads to the explosion. So you heat some, I mean, it's the same thing, even if it was water, which these things boil way earlier than water. Even if it was water, if you generated enough current to heat that over 100, it would start creating gas, and these are obviously enclosed cells. So that's why, like, when you've heard about, like, if you think about it, it's kind of amazing, right? Like, you've heard probably, like, oh, someone's laptop, not someone you know, but just in the news, oh, someone's laptop blew up. Think about how many batteries there are in how many laptops, right, in the world or in phones. It's kind of amazing how few times these things happen, really. And usually when they do happen, the chemistry in them, I guarantee you, isn't any different. It's just somebody manufactured them poorly. And so they didn't, like, create the separation well enough or something. So it's not like they were using some new dangerous chemistry. Nobody does. They're all boring. It's just maybe it wasn't made well, but it's gas production that leads to the explosion. Other questions?
Would rapid charge batteries actually lead to any kind of new applications, or is it just convenience?
Yes. So what I didn't talk about them doing is if you wanted them to, so they could last, the ones I showed you can last the same amount of time as your battery now is. They could, though, if you wanted them to, discharge a lot faster. What that means is they could do things that are much higher power, things that you can't do now. So that's why supercapacitors are used in like buses and stuff. They can be charged really fast. They can give you a lot of power, like enough power to drive a bus. Normal batteries can't do that. Normal batteries can't supply, just like they can't recharge in less than a few hours, they can't discharge even if you wanted them to in less than a few hours. So the ones I showed could, and so they could lead to applications for literally anything where you just need higher power. Like 10 times higher power, a lot. There could be a lot of applications. But.
Could use fuel cells in that application, but again, we're not at the stage where that's really commercial. Yeah.
What about fuel cells? You mentioned that they can be used in the drones. Is there any sort of thought of using those in, say, commercial applications?
It's probably the same thing.
Yeah, it's going to be the same issue with safety.
Right. But you can imagine if, like, in 10 or 20 years, that if their safety record builds up, and they don't, because in principle they shouldn't, then it might be something that.
Yeah, and the drones are also very light. I don't know if that would work. Well, for certain applications, for certain really light things that are basically, I don't know much about how the aerodynamics of it works. I would think for a much larger plane that wouldn't be as feasible.
David,
yeah.
What fuel were they using in the Delphi solid oxide fuel cells?
I think they were using methane. No, it was actually petrol coming directly from the. So what they do is they pipe in the gasoline that comes from the engine, and they do this process called reforming. So you're at a really high temperature in the fuel cell anyway, so you can actually do a little bit of chemical magic and convert the gasoline into other byproducts, things like methane, things like actually a little bit of hydrogen as well. And that's a bit more easier for the fuel cell to use, and that's actually what it is converted. Okay, so that's the other reason these are a bit hard to commercialize is because they can use a lot of fuels, but you also have to have a separate unit for doing this fuel reforming process, something that can convert it into hydrogen, for example.
Yeah. Would you then have a mixture of products coming out?
Yeah, so you will have some CO2, you will have some hydrogen. It's not green in the sense that it's emitting CO2, but because it's so much more efficient than a combustion engine, it actually produces fewer greenhouse gases. Yeah.
What is the size of the hybrid battery we can make now?
What size can you make? So for the ones I showed you, they're scalable, so that you can make any size of one. And these, you wouldn't use them for something like the grid or cars, just because of weight, really, and because of that's a lot of niobium, and so it's going to be kind of expensive. I mean, yeah. You could do similar things that you can do basically anything with these that you do with your battery now. But when people are talking about cars, they're not talking about using the same ones that we use now because they know those are too heavy and they know they're not like. So they're only really looking for lighter things. But these are scalable to anything you make now. Max.
Yeah. So the fuel cells only take energy from oxidation reactions. Like, could you make them work with any exothermic reaction?
It has to be an oxidation reaction that happens in the anode, yeah. Because you're going to have oxygen, O2 minus oxide anions moving through, and it has to react with something. And it's going to have to react in a oxidative way. Because O2 minus is really good at oxidizing things. That's why it's called oxidizing.
Are there porous membranes that work for things, anions other than oxygen?
Sorry?
Are there porous, what are the center part called? That
Oh yeah, the electrolyte. Yeah, so I went through that really quickly, sorry. But
hydrogen, right?
yeah, hydrogen, exactly. Yeah. So if you just have hydrogen as a fuel, then you can use these hydrogen conducting or proton conducting membranes. And you need to have optimized materials for that application, but that wouldn't be possible. Yeah.